Hello again, this is Galen Pickett, Physics 151, Cal State Long Beach. And again, I've got something I want to tell you about Chapter 1. Chapter 1, Section 5, Describing 3D World Vectors. This should be a review for you. This is not the first place that you've encountered vectors. You've encountered them in mathematics classes, other physics classes, maybe in high school. It's a long section to read, but it has got lots of it's got all of the conventions that we'll use and that you will use in your web-assigned homework for this class. It's conventions I'll use as well when we talk about locating objects in three-dimensional space. So, space is three-dimensional. We describe the location of an object by giving it an x-coordinate, a y-coordinate, a z-coordinate. Here is how I will describe a vector in class. I give it a Roman name. So, in this case, it's r. The little symbol, the little half arrow on top of the r, right here, that indicates that r is something that has got a direction and a magnitude. I'm going to write this r as something that has a distance you go in the x direction, a distance you go in the y direction, a distance you go in the z direction. So it's like giving a set of driving directions. You go a distance x along the x direction, then a distance y along the y direction. Now, this wasn't, you can see that the y-axis is sitting back here at the back. I did it in blue. What it really just means is you go in the y direction for a particular length. That particular length is this y coordinate. And then you go upwards a distance z, and you get to exactly where you would go if you followed the vector from the very beginning to the very ending. So that is what a vector is in three-dimensional space. A vector will either give it to you in components, tell you what those three numbers are, or I can give you just the name of the vector and draw it for you. So here's a vector A. It has got a particular length. The vector B has got a particular length and a particular direction. A and B have about the same lengths, but they point in different directions. So vector algebra is what I want to talk about, and algebra is adding these vectors together and multiplying them by scalars. So vector addition is not a new concept for you. The vector A plus B just means first you follow the directions that are in A, and then you follow the directions that are in B. Geographically it means, or geometrically it means, first you do A, so here's where I started off, and then I do this B thing. I make an exact copy of B, and then C is the vector that takes me from the very beginning to the very end. That's what C is, and I can just call this the vector C, which is the sum of A and B. I can scalar multiply A by some value, so A times 1/2, you should imagine, is something that is half the length of A, but it goes in the same direction as A. So again, here is the full vector A. I've got the right to make a copy of it, so here is what the full A is. 1/2 of A is something which is half as long as A, but points in the same direction. So there is 1/2 of A times 1/2. Here's another copy of that same vector, A times 1/2 with a vector on it. If I add 1/2 A plus 1/2 A, you should expect that you get the full vector A back. That is, you go in the same direction as A, half as long, and then half as long again. And so this vector addition thing works exactly the same as this scalar thing does. So you could also multiply a vector by 2. That just means adding a vector to itself. You get something that's twice as long and in the same direction. Subtracting vectors is probably the operation that's new for you, so subtracting vectors. So let me make a new version of A and B. I'm going to say that this is the vector A, and this is the vector B. So that A plus B is a vector that first you go along A, then you go along B. This vector is equal to what A plus B is. So A minus B, you can imagine as so there's the sum, the difference. You can imagine adding A to a vector which is in the opposite direction to B. So I scalar multiplied B by a minus value. This should be what A minus B is as a vector. It's got points in a particular direction in space, and it's got a particular length. So let's do this geometric construction of adding A and B. So first I do A. There's the A. Now minus b is a vector which is in the same direction as b but points in the opposite direction. So here's what minus b looks like. B goes in this direction, so minus b goes upwards. So this vector is what a minus b looks like. First I go along a, then I go along b, along minus b. So there's the a minus b vector. You can commute the order in which this vector summation happens. So I could do minus b plus a, and that should give me the same result. So that should be the vector minus b plus the vector a. And geometrically that would mean first I do minus b. That's the first thing in the vector construction. And then I do the a. And then I go along a. And then the vector, which I would write as minus b plus a, is the one that goes off to up and off to the right. Notice these two vectors, this a minus b and this minus b plus a, have exactly the same length and they point in the same direction, so they are the same vector. There's one more construction, one more way to write this that you should get used to. Let me make a copy of a and b from a common origin. So here is the a, and there is the b from the common origin. The vector which is a minus b is the vector which starts at the end of b and goes to the end of a. This is a minus b. So you draw these vectors not as a vector sum from a common origin, a minus b, and notice this vector that I've drawn here has got the same magnitude and the same direction as this example and this example. It's another way to write what is the what's the difference of two vectors, and you're going to use this almost immediately. So here is an origin in an xy data plane. If here is the initial position of an object, and here is the position of an object at some time t later, the distance it's gone and the direction it's gone is the vector that takes you from where you began to where you end. That is what the delta r is. And from this construction, we see that delta r is exactly the same thing as r of t minus r of 0. It's the same construction here. We've got the two vectors from the common origin, and the difference vector is the one that takes you from where you began to where you wind up.